in real life, at the surface of the Earth, we don't have free fall. In addition to the gravitational force, there is what we call the force of air resistance. We know this, for example, in terms of skydivers. Without air resistance, skydiving would be impossible. What happens is, as skydivers fall and open chutes, they are going to eventually reach a certain velocity that we call terminal velocity, and that's the velocity they continue to fall at, and which is a much safer velocity than the velocity they would have if there were no air resistance. In the same token, if you consider, for example, rain and raindrops would be very dangerous on us and on everything else if it were not for air resistance. Because of air resistance, they slow down and they reach a certain terminal velocity, and they are safe once we walk out and allow them to fall on us. Same, of course, when we talk of to a different degree, hail, for example, it's not as safe as rain, but it would be much more dangerous if it were not for air resistance. So in other words, air resistance can be quite good for us in a lot of different ways. They make raindrops falling on my head kind of an acceptable thing, as opposed to raindrops falling through my head. Okay, now let's try to discuss this. What are the factors that affect air resistance? One of the factors is the shape of the object. A spherical object as opposed to rectangular or triangular or parachute-shaped. The overall shape of the object is going to affect the kind of air resistance force that the object is going to experience. Now, for spherical objects, we can calculate, not at this level course, not for this course, but it's somewhat easy to calculate the effect of air resistance. The more complicated the shape gets, the less symmetry the shape has, the more complicated it gets to calculate the value of air resistance on it. And a lot of times we end up using computers or sometimes just doing measurements through things like wind tunnels and stuff like that to be able to figure out the air resistance on an object. Now, in addition to the shape of the object, there is what we call the surface area of the object. Now, to explain what the surface area is, consider a sheet of paper. For example, if I take a sheet of paper and hold it horizontally so that it's fully flat horizontally and let go of it, it's going to be affected much more by air resistance than if I hold it just from one end and let it fall straight down. Okay, so even the same object, the surface area that's going to be subject, that's going to oppose the motion, is going to be what's going to affect how much air resistance an object will experience. For example, let's take a shape like of a can of soup, a cylindrical shape. If I drop it like this, straight down like this, then the surface area is a rectangle. If I drop it like this, the surface area is a circle, a disk, and so on. That gives you an idea of what we are talking about, surface area. The sheet of paper, the surface area can be like this, or it can be almost a straight line like that, almost nothing. That's what we are talking about. Now, another thing that affects air resistance is the speed of the object. Actually, it affects it different ways. When the object is moving slowly, air resistance is going to be proportional to the speed. Air resistance is going to be equal to a constant times the speed. Now, when the object is moving very fast, like a bullet, it's going to be another constant, let's call it k, multiplied by the v squared. So the faster the object is moving, the higher is the effect of air resistance. But the interesting part here, in both of these cases, that tells you if your velocity is 0, you have no air resistance. And of course, air resistance is due to air, so air density is going to play a factor. Now, the more denser the air, the more air resistance an object is going to experience. Wind is going to affect the way an object moves through air resistance, but usually we treat it separately. I just added it here for completeness. Now, let's discuss in detail what's going to happen when we drop an object in terms of air resistance. Think of a raindrop, for example, falling off from the cloud. The instant we let go of the object, its velocity is 0. That makes the air resistance force, let's call it FAR, is equal to 0. Now, as the object starts falling, it's accelerating. Because it's accelerating, it's going to speed up. Now we have air resistance, because my speed is not 0, so I'm going to have an air resistance force. Now the air resistance force is going to be proportional to that speed. So initially I'm going to have the weight of the object straight down, and the air resistance that's going to be small, opposite to the weight, opposing the motion of the object. Now, as the object speeds up, the air resistance force gets bigger. The gravitational force, of course, that does not change. Now, as it gets bigger, it's going to eventually catch up with the gravitational force, and it's going to become equal to the gravitational force. For a certain speed, the air resistance force is going to catch up with the gravitational force, and it's going to become equal to it. When that happens, what's going to happen when that happens? It's going to balance it, since they are opposite in direction. Once it balances it, what does that mean? No more acceleration. Which means the speed does not change anymore. So the velocity that we reach then, we call it terminal velocity. We call it terminal because there is no change in velocity anymore. Now, because there is no change in velocity, there is going to be no change in air resistance force anymore, since air resistance depends on the velocity. Okay, let's recapitulate here this part here before reaching terminal velocity. We started with an air resistance force of 0, and as the object accelerates, the air resistance force increases. Gradually increases as the velocity increases. Whenever it increases, it balances more and more of the gravitational force. As it does that, that reduces the acceleration of the fallen object, because Fg minus FR is becoming FAR is becoming less and less. Now, eventually, the air resistance force is going to catch up to the gravitational force, and it's going to balance it. The minute it balances it, we don't have any more acceleration, and there is no more change in the velocity. We reach then what we call terminal velocity. Once we reach terminal velocity, there is no more change in the velocity, and because there is no more change in velocity, there is no more change in the air resistance force. So the air resistance force is going to continue at that same value that it reached the instant we reach terminal velocity. And remember, that same value is actually the value of the weight that it just got to balance. So after reaching the terminal velocity, the air resistance force is equal to the weight. Before reaching the terminal velocity, it's going to change from 0 the minute we let go of it till it reaches that weight. Okay, a good question that might come up: does air resistance act on other moving objects? For example, does it act on cars? Of course. It would be much cheaper to drive cars, and they will use a lot less gas if it were not for air resistance. Air resistance is where we waste most of the energy when we drive cars. Does it act on us? Of course. For example, cyclists, they end up, other than wearing this funny kind of clothing, they end up even shaving their hairs and stuff like that to try to reduce of the air resistance. Does it act on objects moving upwards? Absolutely. All what matters is there is air there. Whenever there is air and you are moving against it, there is air resistance. Now, of course, the terminal velocity issue and so on will be different if an object is moving upwards. Moving at an angle, same situation. So as long as you have an object moving relative to air, we have air resistance. Now, one question that might cross somebody's mind is: air resistance what makes airplane fly? And that's a no. That's something I'm not sure we'll discuss in this course or not, but that's something dealing with fluid dynamics, or what's called the Bernoulli's effect, and we'll see if we'll get to that later on. But it's not air resistance that makes an object fly. Air resistance is whatever is going to slow down an object, it's friction. And along with other airplanes, other than air resistance, there are a lot of things that involve air that affect the motion of objects. For example, the curve, when we talk of aerodynamics, when you think of a baseball ball, for example, it's not a smooth ball, and we purposely don't make it smooth because of the aerodynamics of that ball that way. And somewhat, if we give it a spin, we can have some aerodynamics effect that's going to cause the ball to curve. Same with tennis balls. That's why we have those fuzz on the tennis balls. And you can think of frisbees with another application. You can think of golf balls. The dimples on golf balls are not there randomly. They are there to allow the ball to have that curvature, to curve while in flight, for aerodynamic properties. I'm not sure we'll get into more of that in this course, but it's worth noting that it's different than air resistance. One good question that I ask often, and I ask almost to all classes I teach: what is the shape of a raindrop? Usually I ask the students to draw it. I'm not going to be able, I'm going to still ask you to draw it, but I'm not sure if you'll do that here when we are doing this online. But I'm sure you will know what shape you have thought of. In my case, most of the students would draw something like this. And what I immediately tell them once they do that, I tell them that they watch a lot of cartoons, and we get everyone to laugh and so on. Okay, and now why do we have this shape? It's because TV kind of shows us rain falling like this, and kind of a sadness associated with the rain. The raindrops that way kind of look a lot more like tears that we can see more easily. But the tears, they have this part because the tear, when it is dropping on our faces, it's actually it is sticking to our faces. There is adhesion between the liquid of the tear and our face, and that's why it's going to take that shape. However, in rain, it is falling in space. It does not have anything to hold on to it or to stick to it to result in a shape like that. So this is not the correct shape. Now, what's interesting, if you look at the universe, what's the shape of the Earth? Spherical. What's the shape of our planets we see? Spherical. What's the shape of the sun? Spherical. Objects, naturally, and this might take more advanced physics to learn that, but the shape that objects would take naturally, if they don't have additional forces acting on them, is going to be the spherical shape, because the spherical shape will result in the least amount of interaction between the matter making up the object and the outside. Now, if it is water, it makes the spherical shape would result in the least amount of interaction between the water molecules and the air. Now, so that's the lowest energy shape. So because of that, objects, naturally, if there are no forces, no other forces to affect their shape, are going to take the spherical shape. And that's going to apply to raindrops. And actually, that's not the full story. I pulled up some pictures of the web. Okay, now here, I'm not sure about the quality of the pictures, especially in the way you see them. If they are very tiny, the raindrops, they are going to take that shape, spherical shape. Now, the larger they get, the more complicated it gets. Now here, if it is 2 millimeters, you see it kind of flattens. The website that kind of talks about that calls them rain burgers. Why is that? Okay, think about it. The raindrop is not a solid kind of surface, so you can affect it very easily, and it is pushing against the air here. That's pushing up on it. So the air is going to flatten that surface. Okay, we have a drawing here that tries to emphasize that. So we have a higher pressure of air that tries to flatten the surface here at the bottom, but then it's not going to flatten it on the top. So it's going to act like a flat surface on the bottom and a curved surface on the top. That's why we call it a burger shape. Now, as the shape gets bigger, the bottom here is not going to remain flat anymore, and eventually kind of it breaks, and we have this more complicated shape, and it breaks into smaller raindrops, and going back to this situation again. What's interesting, people didn't know this till probably about 50 years ago now or something like that. I think in the 60s, that's when people realized this part, the 1960s, and it took longer to figure out all the rest of the details. Now, a few questions dealing with air resistance. Which would experience a larger air resistance force if they fall from the same height, an elephant or a mouse? Of course it is an elephant. Why is it an elephant? For two reasons. First, it has bigger surface area. Second, it has a bigger mass. If it has a bigger mass, that means bigger weight. That means it's going to take longer for the air resistance force to catch up with the gravitational force. It's going to take a much bigger air resistance force to catch up with the weight of the elephant than with the weight of the mouse. So we get a much bigger air resistance force on the elephant than on the mouse. An alternative to this question is comparing the elephant to a feather. and the same answer applies. The air resistance force on a feather is so tiny, the gravitational force is so tiny as well, so that's why you see a feather reaching terminal velocity really quick. Now, which would reach a higher terminal velocity? Again, it's the elephant, because it's going to take much longer for the air resistance force to catch up with that large gravitational force that's acting on the elephant. Again, here, what if they have the same diameter? We have two spheres, same shape, same diameter. Which one will experience a higher air resistance force? A ball and ball or a soccer ball? And the same answer applies. Ball and ball has a larger gravitational force, larger mass, so it's going to experience a larger gravitational force. Because of that, it's going to take much longer for the air resistance force to catch up with this gravitational force, to balance that gravitational force. So it means we reach a higher air resistance force and a higher terminal velocity.